2 more classes, huh? Crazy. Now, so we have covered so far like about 200 years of the work of many, many, many people, including the many poor grad students who do these formulas you don't need to redo. That's the reason we don't need to solve differential equations, not often at least. And you don't need to do integrals and crazy stuff. Now, what have we seen so far? We have seen these energy balances, if you remember, right? Then we talked about heat transfer mechanisms, and we talked about conduction, advection, convection, and radiation, right? And then we started with conduction, and we came up with a concept of thermal resistance, right? And we talked about conduction through thick cylinders, even spheres, right? Which came in handy if you look at problems on heat exchangers. If a heat exchanger has, for example, thick tubes, those tubes we should calculate using these formulas from conduction that we saw at the very beginning of the class. Now, after that we said, okay, let's extend this understanding of conduction to conduction through the boundary layer, and that is convection, right? There is motion of fluid far outside, and then right next to a surface, the fluid becomes stagnant, and we conduct heat through that thin layer. Right? So if we understand this boundary layer, we can understand pretty much everything about conduction. And we spend a lot of time looking at conduction in external flows, conduction in internal flows, conduction with natural flows. We even looked at convection with phase change, right? Things are pretty crazy, so much we did. Then we talked a little bit about how it all came together on heat exchangers. And we saved radiation for last. That's a traditional way of doing it. There are heat exchangers with radiation, but for the most part, we did heat exchangers only with convection, and we're going to see radiation today. So today and Wednesday is radiation. Lots of new concepts. And if you look at past final exams, you're going to see that we do ask problems on radiation. If all goes right, I want to do the concepts today and solve a problem for you on Wednesday, 1 or more. Something interesting about radiation, right? You know how you cool a car on Earth, right? You have a radiator, which actually, funny enough, doesn't radiate anything. It just has like convection, right? Is a heat exchanger between the hot water of your engine and the cold water that comes in through the air. You go to the moon. How do you cool the engines now? It's not a combustion engine, it's electric engines, but still generate heat, right? Even more. You have heat, sunlight coming into the vehicle. So how do you get that energy out? Because it's not that the wind is going to take all that heat out, right? So it's very interesting. They had a problem. Funny enough, to deal with the engines, what they did is to put some heat sinks. In a heat sink, what happens is the heat starts to accumulate in something that has a lot of specific heat, right? So they couldn't run it all day if they wanted, because as the heat starts to accumulate, you take it out of the engine, you accumulate it elsewhere, but there are limits to that. So this is a pretty interesting thing, and it gets us thinking about radiation. Radiation is like nothing we have seen so far, because both, we said conduction is easy. One atom gives energy to the next atom and they propagate. It's okay. Convection in the end is conduction through a boundary layer, so same concept. Now, radiation is the energy goes through a vacuum. How? I have no idea. But nobody has an idea, right? That's why people invented at the beginning of the 1900s the concept of ether, right? Because they said it cannot possibly, like James Clerk Maxwell, he of the Maxwell equations, right? He came up with this concept of ether because said energy just cannot go through a vacuum from one end to the other. So it has to go, one molecule affects the next molecule, affects the next molecule. But they didn't see any molecules. So they came up with this concept of ether, in which you would have a means to transmit this energy, right? Even if you don't see it. Today, we say it's vacuum. And if you push me, I don't know exactly where the ether breaks down and where the vacuum gets real. People in physics even argue that vacuum is not really vacuum because you have energy in the vacuum. I don't know. But from the point of view of heat transfer, I'm going to tell you many things in which the main difference is that radiation goes from that wall to that by radiation, even if we were in complete vacuum. Very different than everything we have done too. There are many other things. Remember, we had conduction in 1D, 2D, 3D, right? Well, radiation is 4, 5, and 6D. Crazy stuff, right? How can it be? But I'm going to show you the 4D. But so let's start with a few concepts I'm going to bring up. So concept number 1 that is going to help us simplify things is radiation is an exchange of heat, right? By electromagnetic waves. You could have something hot that is radiating. For example, a flame. In a flame, you have gas that is so hot and emits, and each volume of the flame is emitting, right? So right there, to account for radiation from a flame, you need to do a triple integral over the volume of a flame, right? And I'm not even saying where this flame is, this heat is going, right? And similarly, if you have a medium that is semi-transparent, right? Some of the heat goes through and some of the heat gets stuck. So in each element of volume, you would have an amount of radiation that is coming in. And the radiation can come from any of 3 directions. This is the left, the high temperature gas or semi-transparent medium. On the right is radiation that comes out of a surface. For example, I'm warmer than that wall, so from the surface of my skin, I'm losing heat to that wall, right? So that would be, if these arrows indicate the emission by radiation, in this case, the emission is only like this, like half a sphere, right? So this is what we're going to be looking in class, right? At radiation from surfaces. But for example, in the case of welding, that is my field, this very intense plasma arc, you have to do the integral in the volume, and you have to calculate it that way. Another thing, for conduction, thermal energy is thermal energy. What part of heat you don't understand, right? But for radiation, so like energy comes in different colors. And this is literal because you have different wavelengths. So it's not the same to transmit thermal energy at 10 microns wavelength or at 0.1/10 of a micron in wavelength. Not the same at all, right? And has many implications. Now, radiation, right? We talk about thermal energy, and we're going to calculate energy balances and all those things. But when we talk about radiation, we are also talking about light, right? The light is not only what we see, but can be infrared or can be ultraviolet. The light we see goes between 0.4 and 0.7 microns, right? It's a 0.3 micron window, very, very narrow, what we get to see. And you're going to see that is what we see is not a coincidence. We see what we see for a reason. Now, longer wavelengths is in the infrared, right? And so is the thermal energy we don't see, but like if you have like night vision goggles or something like that, well, not night vision goggles, like infrared sites, you could see, right? You could see this radiation emitted, right? But we don't see it with our eyes. And shorter wavelengths than that is ultraviolet. Ultraviolet, that is the one they sell you these sunglasses, and they say make sure you filter ultraviolet. All right, that is shorter wavelengths than what we see. Right? And then, of course, you can go to the right, very long wavelengths. You start getting into microwave and radio frequencies, right? And shorter than that, you get into beyond the ultraviolet, you get into the X-rays and the gamma rays and things that are not so used for heat transfer. So here's where we live more or less, between 10 to the minus 1 micron and 10 to the 2 microns. We're going to see why. Right? So not only the transmission, the different wavelengths give us different properties, which was not the case of conduction. But in addition, when we talked about conduction, the way the heat moves, it follows a gradient, right? But in radiation, it's not like that. Hot gives a surface emits radiation in many directions, independent of who's there catching it or not. Right? It's a completely different concept, and this is one of the reasons this unit appears at the end after we have talked about everything else. So there are two important variables as we talk about radiation. One is wavelengths. So when we talk about, this thermal energy coming out. Okay, one of the very important questions is, okay, thermal energy at what wavelength? That's going to matter. We're going to see. The other question is, when we emit emit energy, we emit normal in a normal direction, and you're going to see things called normal emissivity, for example. But you have emission sideways too, right? And we're going to see how surfaces can be diffuse or specular. I'm going to mention that. But what matters is two things that we did not care about in conduction. One is what's the wavelength, and the other is what is the direction from the surface at which we're emitting. So here there are four concepts. And these four concepts, this is a very wordy slide, but it's straight from the book, is things with which you are more or less familiar. So let's start with E, emissive power, because this is one we have been using so far. E is radiation emitted by from the surface. It's emitted, so you're above 0 Kelvin, therefore you're emitting energy, right? This is E, and epsilon sigma T to the 4. You already knew that. This is what we've been using so far. Irradiation is how much energy comes into the surface. For example, you're out there in the sun, you're being irradiated with the energy of the sun. I have a laser aiming at my weld, so I'm irradiating that laser, right? So it's a concept we have not used so far, but it's a concept easy to relate to. Now, this other funny word, radiosity. Radiosity is, I don't know why they called it that, but is all the heat that goes out. And the concept is easy to get a hold on, because we were talking about how much energy is emitted. But if I'm a reflective surface, not only I emit by thermal radiation, but I also reflect some of what comes in, right? So, for example, if I'm aiming at a mirror, some thermal energy is going to bounce back even if the mirror is cold, just because whatever comes in is not absorbed and comes out. So that is radiosity, all those two things out. This is essentially a Q out of a balance, right? Energy out. And then the net radiative flux, right, is irradiation is what comes in, Q in, this is the Q out, and the net radiative flux is whatever came in, right, whatever is going out, right, in whatever ways it goes, minus what came in, right? And the difference is going to tell you if heat is being absorbed by radiation or being emitted by radiation. Right? This is what these four terms are about. And we're going to see there are formulas associated with them and that help us calculate a Q in minus Q out from the point of view of radiation. You get to see them here. I don't want to distract ourselves with formulas right now. So there's another concept that is an idealization. Remember how we've been using spheres and cylinders, right, and plane walls, right? Those are idealizations. The reality is always more difficult than that. But when we understand a cylinder or a sphere or a plane wall, then we can relate our reality to that idealization, and for the idealization we know how to deal with. Now, radiation is a very different thing. Not only we're going to have spheres and circles and those ideal geometries, but we are also going to have an idealization about this distribution of energy across wavelengths and across directions. And this is the black body radiation. So the black body radiation absorbs all the energy that comes in and reflects nothing. Also, when it emits, right, emits in a very particular way, which we are going to discuss, that probably you already saw in Physics 1, right? Have you seen radiation? No? Physics 1, maybe? Don't worry, we're going to do as if you hadn't seen it, right? And we are also going to say that the emission from the black body is a diffuse emitter. I'm going to define this in a few slides down the road, right? And there are ways of approaching this black body, for example, by making cavities in which, if the light comes in, starts bouncing crazy inside and doesn't come out, right? Those type of things. Those are approximations. This concept of black body is a concept that was developed from physics, right? And is something we're going to pick up and we use because it's very useful, right? But this black body, why we can say, for example, that at a given temperature and wavelength, you can never emit more than a black body. All those things are things that would come from physics. But in our idealization essentially is, let's assume reality is a black body, and then we're going to use some correction factors to accommodate it to our reality. The first correction factor you're already familiar is the emissivity, right? We say things don't emit as much as a black body, emit epsilon times that, which is epsilon was always less than 1. Okay, so some interesting things about, I'm going to talk now about the black body. And reality is not exactly a black body, but reality is close to a black body so often that if we study a black body, we're going to understand many things of reality. So in the horizontal axis, we have wavelength. And the vertical axis, we have the emissive power, right? This is how many watts per square meter we're emitting in all the directions. And they put it here per micron of wavelength. You see, so this is, for a given wavelength, you emit this much. For another wavelength, you emit that much. For another wavelength, you emit that much. If you integrate over all wavelengths, you get the standard sigma t to the 4 that we're familiar with. Now, what is interesting here, and you're going to see how this relates to real life more than you ever thought. This is the range in which we see, right? This is the visible light. Here we have infrared. Here we have ultraviolet. What these curves represent is, for example, let's pick this one that says 2000 Kelvin. The 2000 Kelvin curve says that if a black body is at 2000 Kelvin, is going to emit so much energy at this frequency, is going to emit, let's say, 10 to the 4 watts per square meter a micron, right in the middle of our visible range, right? It's going to emit a little bit more in the infrared and so on, okay? Now, these curves have a peak, right? And this peak lines up with this line. If you see this axis here is log scale, and this is also log scale. And look at this, 10 to the minus 4 to 10 to the 9, right? There are, how many zeros we have there? 4, 5, it's like 13 zeros of difference in emissivity, from emitting close to nothing to emitting 10 to the 13 times that. So the peak is here. This is what we would see. Interesting things. Surface of the sun. Surface of the sun is more or less at 5800 Kelvin. Right? That's the surface of the sun. Where is the peak? The peak in emissivity for the temperature of the sun is right in the middle of the visible. For those of us who believe in evolution, that means we evolve to see what the sun is showing us. This is super interesting, and I'm going to show you more things that relate to this. Now, this is what we call white light, and all the wavelengths we see have more or less the same power. Look at this. If instead of that I might say 1,000 Kelvin, right? 1,000 Kelvin would be 700 degrees C. Things start to glow red hot when you heat up at 700 degrees C. Look, this at 1,000 has a lot of emissivity in the red and very little emissivity in the blue. And look, by a lot and little, I'm talking about like 4.5 orders of magnitude difference. No wonder at 700 C you see things red. And then you increase temperature more and more and more. And now the difference is less and less. Here we have 4 orders of magnitude, we have 2 orders of magnitude here. And that's why things go from red to yellow to eventually we say something is white hot. In reality, when we say white hot, is in comparison with the red hot. But it's still, when something is white hot, that would be like here. Still, if you were to do a spectrum, there is more red than blue, right? The sun, when you see this harsh light from the sun, has a lot of blue components. And there's a formula to calculate where this peak is going to be. That is more or less 3,000 over temperature in Kelvin, right? So look at this. When I said this relates to real life, when you go buy lamps at IKEA or whatever, you see that the lamps come with this type of thing that they say this lamp is a 5500K lamp. Yeah, have you seen that? When you go buy like the LEDs, when they say soft white or bright white, right? Okay, you pay attention to that. What you're going to see, haven't you ever put 2 lamps and they actually look odd? Sometimes one looks bluish and one looks reddish. That's the reason, because these lamps are replicating different temperatures. And a lamp that is at 5500K would have the peak. This is designed to have the peak and emission similar to the sun. So those are like the daylight lamps. Now, a lamp that is 2700K, right, is the reddish, like indoor, like those lamps that are like calmer lamps. This is more like surgical room lamp. This is like a lamp to hang out with friends, right? If it is 2700, all of a sudden you start to see how it has more of a red component. For example, I love these bright white lamps. I see everything clear. My wife loves the red ones. And you cannot negotiate. You cannot go half and half. It looks horrible, right? More, those of you who like photography, how many of you uses a digital camera other than your phone? See? Okay, if the phones also do, like when you do color correction, the color balance, did you see the units? They're often something K. The something K goes back to this Wien's law, right? And this is from a photography page in which they say, okay, depending on what your temperature would be, this is Wien's law, is what type of color balance you're going to see. Have you ever taken a photo from inside in which you see your house and then you see a window? Have you seen that the window typically is blue and the house looks red, or if the house looks white, the outside looks blue? Do that. It's super funny to see that. We ourselves, correct, we say this wall is white, but if we had light from the sun, we would see it a lot whiter than it is, right? Anyway, the whole point here is how this thermal energy, and in our case, what we see, right, is like a little sensor into that window. This gives us different, it behaves differently and gives us different colors. Let's talk about real surfaces. I mentioned there are 2 important aspects. One is wavelength, and the other was directionality. So this is the emission from the black body. The peak here is 3,000 over temperature in Kelvin, right? This would be Wien's law, and this is Planck's function, and if you integrate it, gives you the sigma t to the 4. Now, reality is not just this. This is a black body. Reality is less than this, and the less is kind of odd, right? So what we are going to be doing is saying reality that looks like this, different emissivity at different lambda, we're going to say is actually a black body, but lower. That's the epsilon. When we say epsilon sigma t to the 4, sigma t to the 4 would give us this. And the epsilon would say, okay, let's say that this squiggle is actually this same thing, but lower. Right? That's what we're doing. There's another thing. Black body, a real surface doesn't emit all the way in all the directions, right? But a black body does. So when we do our approximations, we're going to say that in reality, things emit in the same way. The black body emits in the same in all directions, but we acknowledge that directionality plays a game. So look at this. If we have a non-conductor, the conductor and non-conductor refers to electronic conductor, like a metal. And the shiny aspect of the metal and the color of the metal comes from this the cloud of electrons that reflect light. So a non-conductor doesn't have that cloud, and the emissivity is close to 1 and then comes down as we come at shallower and shallower angles. Now, for a conductor like a metal, emissivity is low, right? And as we approach, as we approach the shallower angles, starts to go up and then goes back down again. So these things make it very difficult. To give you an idea, when a guy comes to do drywall inspections and comes with a thermal camera, if you say, okay, give me a temperature, they couldn't easily do it because they need to assign an emissivity to give you a temperature. And that emissivity depends on the angle, depends on wavelength, depends on many things. Very tricky. So when you're getting into these issues of thermal imaging, you better know what you're talking about, because it's always pretty, but that doesn't mean you know what you're doing. Spectral emissivity. So now we are talking about real surfaces, and we dock them with an emissivity coefficient, right? We say, let's say that a real surface in reality is a black hole, and then I correct it with emissivity. And what these curves you see here is for different wavelengths, what emissivity you should attach to that one wavelength. Right? So, for example, the emissivity of stainless steel at 0.4 microns emissivity, that would be blue, right, is 0.6. But the emissivity, when we are just above 10 microns, that is deep into the infrared, is much lower, is 0.2, right? So that we're talking about part by part. So these emissivities, this curve that says spectral emissivity versus wavelength, that is more or less constant with temperature, more or less. Look at this. It says normal emissivity. So they are looking at emissivity just face on, right? No, they are not saying anything about the angle at which we're looking at. All right, but overall you get to see it goes down. Here you have like aluminum oxide. It is very very emissive in the infrared. Many materials have crazy properties. So when you look at things like spacecraft, that they need to deal with radiation a lot, they use very exotic materials because they want these peaks and valleys to be exactly where they want them. And that's not trivial. Now this is total normal emissivity. So now it's not spectral anymore. I integrate over all the lambda, and here I have temperature. And now guess what? I just told you it didn't depend on temperature. And now I'm showing you curves that say how stainless steel is changing with temperature. Who can tell me what's going on? I'll give you a hint, I did not lie. So let's look at this. As we move to higher temperatures, right? Wien's law tells me I'm going to putting emphasis on shorter and shorter wavelengths, right? I'm moving from the infrared to the red to the blue to the ultraviolet, right? So look here. For example, if I were to do this integral, right? And I would have at low temperatures, let's look at stainless steel. At low temperatures for stainless steel, I would be looking at emission around these wavelengths, right, for low temperatures. But at high temperatures for stainless steel, I would be emitting at these wavelengths. So this is the emissivity that would go with low temperatures, and this is the emissivity we should use with high temperatures. You see? Low temperatures, low emissivity, high temperatures, high emissivity. Yes?
So like, what is the emissivity of silicon carbide at 2700 Kelvin? Does it stay at 0.8?
At 2700 Kelvin?
Yeah.
I cannot tell you because the book didn't tell me. Oh. But I can go and try to find it out, right? Like, so these values here we have are very approximate. Have lots of books. When MIT was divesting from its library and going digital, I got to keep the book on thermal emissions. It's a huge book with emission for whatever you ever want. So if you want that answer, I'm sure I can give it to you, but it's not in the book. So you get to see these things. So the point here, we will do some calculations. I will ask you calculations in the exam. But as you guys ever need to deal with radiation, to be aware that different temperatures give you different wavelengths, and these different wavelengths behave differently. There is so much more to say. So here we have total normal emissivity. This is what we have been using so far, right? And we already see something funny, because if you want to make a calculation and you're talking about shallow angles, this is not really true. But you have to be a specialist to worry about that. So we talk about normal emissivity as if it is the only one that was. And what do you get to see? Pretty much everything is close to a black body. Like skin, doesn't matter how blonde you are, you're close to a black body anyway. So don't go to the sun and thinking you're going to bounce off the rays, because it doesn't work like that. Mineral glasses, right? All these things are close to 1. Of course, the book gives you this range because oxides and ceramics, tell me which one, right? But then, if you have polished metals, the emissivity is very low. So overall, the way I see things is like two things. Polished metals are close to 0.1 or less, and everything else is close to 1, right? If you want to get like finer than that, we can use this book I have, and I have many others. But essentially, are you a mirror or you're not? Look at this. This is I coached a Science Olympics team a few years ago, and I had a guy from NATE come with a thermal camera. We didn't have ours then, but now we have one much better. And the guys needed to make a thermos. It was so awesome. And they got a gold medal, by the way, so it wasn't that bad. And so this is a thermos they needed to do, and I had this kettle. The focus here is on the kettle. The kettle had boiling water inside, so it was all hot. But look at this. This is more or less the same temperature. But the lid looks as if it is like super, super hot, right? The body looks as if it is lukewarm. In reality, and I know because I put my finger there, it's more or less the same, or burns you more or less the same. Why is the camera showing me this difference if I tell you that the temperature is more or less the same?
It's shiny metal and emissivity.
Right, this is shiny metal, so it's emitting very little light. So the camera, I think, is the way a thermal camera works is it looks how much heat it comes into it and says, oh, if I got this much heat, therefore I have this temperature. It's a pretty dumb thing, and I paid like $150,000 for one of those. I cannot believe it. But we're trying to spend that much money again on something else. But So, and here, this is plastic, right? It's close to 1. So this would be like 0.1, and this is 1. And guess what? Now this plastic is emitting radiation like crazy. And the dumb camera says, oh man, this has to be real hot. So part of the catch of all these things is you gotta know how to interpret these things. It's pretty, but prettiness takes you only so far. Look at this. This is the water being dumped. It looks like molten. I don't know if you guys ever saw like pouring of iron, steel. I used to run a foundry when I was a professor in Colorado. Looks exactly like that. Exactly like that, right? That's because it's very hot. Something interesting. This water doesn't look transparent at all, right? And I told you that for infrared radiation, liquids are essentially opaque, right? Let's talk about reflectivity. There are two ways of reflecting light. One is what is called specular reflection. That means like mirror, right? Light comes in and light goes out. Right? This is a principle of the stealth planes, right? If you get the radar in, it bounces it off, and nothing comes back to the radar. In reality, for a black body and most other surfaces like this wall or skin or pretty much everything we see that is not a mirror, light comes in, and gets scattered all around. Right? This is what is called a diffuse emitter. Let's talk some more about reflectivity, and these are like diffuse surfaces. This is super interesting graph. It might not look like that to you right now, but horizontal axis is wavelength, always the same, 0.1 to 100, right? Is where most thermal radiation is for us on Earth. Here we have reflectivity. How much do we reflect? So let's look at this. Black paint. Very low reflectivity, right? As it should be. I like it. But here we have some interesting things. Look at this. Snow. And visible light is between 0.4 and 0.6. Snow is essentially a mirror, right? That's why you need shades when you go skiing, right? Those people who, the Eskimos used to have these special glasses to prevent the reflection, right? People who crash in the Andes needed to make fake sunglasses because otherwise you destroy your eyes. But let's look at snow, because this is super cool. Snow, you would say snow is white. Yeah, until you get into the infrared, like 2 microns. At 2 microns, snow is as black paint. Isn't this awesome? Right? So the light from the sun bounces off the snow. But if the snow is next to the hot wall of a building, all that heat that is coming from the wall, the snow is sucking it up all right. Isn't this interesting? So, no more Snow White for you. So, same with white paint. Yeah. What's white about paint? About 5-6 microns. Nothing. Right? And all these things are important to know, at least to understand, as you're looking at thermal radiation, because you would think glass is transparent, water is transparent, snow is white. Not true. Not true when you look at it from radiation at large.